Good morning. Can you hear me okay? All right. It's kind of early. I don't want to talk too loud to some folks. Good morning to all of you. I'm Gary Kern with the Schooler Company. I'm the loss control manager out of Salina, Kansas. While many regulations have changed, the principles and the physics for dust collection have not changed, but the methods and means have. Our next speaker will teach you how to design new and existing transfer points, origins of dust generation, to have less dust collection requirements, and therefore less air emissions. You may also decide if smaller, more efficient collection is your best solution, or reviving the current capital investment to its once former glory. Helping with the decision-making process is Andrew Knapp, a registered professional engineer with over 20 years experience in project management and engineering design for grain and material handling systems. This includes conveyors, loading and unloading systems, storage and reclaim, dust suppression and control, and other systems at elevators and grain terminals. For the past year, he's been a senior project engineer for River Consulting and has also worked for other engineering companies, but also as an engineering manager for S. Mueller Company, as an applications engineer for InterSystems, and as a senior project engineer for Screw Conveyor Corporation. Andrew holds degrees from the University of Alabama at Birmingham, Franklin University, and has a master's degree from the University of Phoenix, where he has also served as a faculty member for 2 years. He is an active member in the Hoosier chapter of Jeeps. He will be visiting us today about dust control systems, a challenge that he has helped many clients address, which work across a broad span of industries that have dust issues. Please welcome Andrew Knapp.
Thank you. Thank you. Thank you guys for having me here today. Like the speaker Bill yesterday, I'm one that likes to get up and move around. And I'm going to give you a little forewarning. The last time I did a presentation at first thing in the morning, I had some difficult things to eat the night before, and so I made it 3D for some of the people. So I'm going to make sure I'm right here in the front area, so the guys that asked me to come here, should things happen, I'll just make sure that we get the 3D effect right in this area. So like we talked about, dust control and dust collection. Let's see, there we go. Applying new technologies to new facilities and retrofits. What we talked about earlier with the NFPA codes, if you're building a new facility, some of it is, there is no retroactivity. This is the code you got to follow. In certain situations, the retrofits is where you may say, you know what, I don't necessarily have to follow some of this stuff. So we're going to be looking at these different things. We're going to run through the who, what, why, when, and where of this. So who does a facility benefit applying these new technologies? Why is it a good idea to update? What are some of the new technologies? There's a lot of buzz going around about some things that are new. Some are just repackaged ideas. And when is it a good idea to update? When is it saying now's the time, now's the right situation? What events have occurred to look at? Where is the best place to update these new technologies? Everyone may think, well, it's dust collection. It's your dust collection. Is it? Maybe. How is the best way to proceed with these updates and technologies? There's several different paths on almost any topic. You ask one person, they got an opinion. Ask another, they've got another. Ask a manufacturer, they got one. Ask an engineering company, they got another. Ask your corporate accounting groups, they got a third. So, who does this dust control benefit? First, foremost, I guess the facility employees, quality of air, quality work environment. Who would rather work at Disney where there's like hardly any trash on the floor, or scoop out a bucket elevator pit? So if it's nice and clean, it's the happiest place on earth. Your elevator could be the happiest place on earth. Kept it clean as Disney. Facilities operations, keeping the dust in the material. Well, if you keep it in the material, it's a clean place. You keep it in the material, operations don't have to worry about maintenance. There's not a lot to maintain for the dust spillage. Maintenance, well, now they don't have to clean up the dust. They can just worry about preventive maintenance. Going on the stuff that they want to watch versus the stuff that has caused accidents, has caused, downtime that they're not, looking forward to. And of course, the company's balance sheets, lower cost of operations. You get to sell the dust. That's a commodity, whether it's in the dust or in your overall weight that you're selling out. As we were learning yesterday, OSHA's been creeping around. There's fines that are going on. And lower cost of insurance. I've asked some of you guys around here, and I haven't quite heard that as much in the grain about insurances raising rates due to finding some unsafe practices. The previous industry I was in was the power industry, and a lot of insurance companies were making the power industry upgrade to IMSHA-style belting, to very various safety devices that were not really required. But for them to get insurance and pay for it, they had to be upgraded. So I don't know if you guys have faced that yet or not, but it's something the power industry is been seeing. And some of this technology that we're talking about, the power industry has had to comply because of the OSHA environments. So why do we improve this dust control? Well, most of you guys probably know this, but we don't want to have a grain explosion. So here's a nice little video kind of giving you a little demonstration about this.
Do any of you guys know what it takes to explode a grain elevator? It takes a spark, ignition, dust. That's our fuel source. Anything else?
Oxygen.
Oxygen, yep, and confinement. So you're going to find all four of those in any regular elevator. You're going to have your confinement, you're going to have your oxygen, you're going to have your fuel pretty much. Your fuel and ignition, that's what you gotta watch for, because those two things you can try and work at. You want to keep your dust below 1/8 of an inch, because any more dust, you're going to have an ignition source. Fuel, you can get that ignition source, from your equipment just working it. It can get sparks going. So what we're going to show is this is going to be the actual dump pit leg, the elevator. You're going to watch the fireball. It's going to spark right here. You're going to have your first explosion in the gallery. That's just your first small explosion. The main explosion is going to be your secondary explosion. It's trying to find a way out of the elevator. So this is going to be our annex. So this is where the big fireball is going to come from.
Are we standing too close?
Nope. I am going to blow it, so just an FYI. That is 1 teaspoon of flour that we use. That's all the amount of dust you need to explode. 1 teaspoon.
Do it again.
While these demonstrations are nice and the ladies just do it again, it's fun to watch there. I think that's a great little model everyone should have. They should have it around to definitely show new people in the industry. But like she said, 1 teaspoon. So these little packs of sugar you put in your coffee, that's basically what that explosion. If we all had one of those little packs of sugars, we took it right now and threw it up, would we have enough containment? Would we have a spark? But what you put in your coffee can cause that kind of explosion. So why do we do it? We want to prevent these things. And I know that several of this next slide here, some of you guys may remember this event. I remember this event because my father was just there right before it blew up. But this is something this is the real world.
Pierce was 10 air miles away from the explosion of the $100 million Continental Grain Company plant in West Wego. The blast destroyed the grain elevator and also 48 of the 73 grain silos used to store soybean, wheat, and oats. "36 lives were lost. Most of the 11 survivors were near the silos, but James Stansberry was one of those who lived through the blast inside the grain elevator itself.
I was thrown through a wall because that's the only way I could line up where I was. I had to go through the wall to get where I was. And I figured, well, somebody must be out there, so I started hollering, "Please help me. Won't someone please help me?"
Miraculously, he maneuvered himself out of the wreckage and onto the top of one of the burning silos. His rescue was filmed by ABC News.
Lieutenant Commander David Scott flew one of the most frustrating missions, trying to drop a rescue basket to a man named Flowers Wilson.
You could see it bouncing off several pieces of that rubble when he was trying to grab it. And, of course, trying to hold the helicopter steady in the black smoke somewhere between 50 and 100 feet above him. And the updrafts from the heat coming off the fire made it difficult to stay in one spot. Most of the times that he was getting a hold of it, we didn't realize that he actually did, because he was only visible part of the time in the smoke.
Finally, Wilson jumped 15 feet to a conveyor housing. Firemen reached him then, and he was lifted off by the helicopter. He is in intensive care today.
So this is the real-world application on why we need to improve dust control and dust collection. While the other one was a neat little example and was kind of fun, this is what we're trying to avoid. And some of the new regulations we're talking about, the NFPA 652, about the explosions and trying to make a structure resist an explosion within the immediate area. It's so, guys, I guess they don't get blown through the walls. So when we're looking at a holistic approach to this stuff, we're not just looking at it for maintenance and for operations. We're really looking at it for life safety. That's the primary number one reason why we look at this. It may cost a lot, but it can cost even more. Government regulations is another reason why we do this. Coming in auditing, they can come in and audit. You're building up a new. The question comes down to which government regulations are we going to look at? Which ones are mandated? Which ones are suggested? Which one applies to your facility or which area you're upgrading? Engineering design. You ask us engineers, and boy, we'd like to design it so you guys can't afford it, but it'll be cool and it'll be nice. Plant management, they've got to, get costs down, billings up, cash flow through. Accounting likes that. So when we're looking at all these things, why do we improve it? It really should be, similar, well, maybe plant management engineering can be swapped, but similar to a top-down look at life safety, number one, government regulations. So, and again, the insurance, haven't heard too much in this, but in the power industry, that has become a huge lobbyist. So when we look at the government regulations, which one do we use? We've heard, earlier yesterday between the NFPA 61, 68, 69, 654, and the new 652. So these can be, very daunting when you're looking at, facilities, which you're upgrading to. Actually, you have to read through quite a bit of this stuff to figure out, does it apply to my facility? Where does it apply to my facility? Again, you ask engineers, and all this applies. Engineering groups are going to cover their, risks. But when you really need to look down to it, when we're upgrading, let's look at, retroactivity. Unless otherwise specified, prior to the effective date, and where specified. So that's your first thing. When was this regulation upgraded? When was your facility built or this part added on? Is it specified? And where is it specified if it is? Then you got to go down to, okay, well, who's going to enforce this? Who is the authority having jurisdiction? Is it your local fire marshal? Is it the EPA? Is it now OSHA coming in? Who is this authority? And this can have a huge effect on, do you upgrade or do you not upgrade? If you've got a major upgrade going on, and for example, you have some areas that, they've been safe for 50 years. And I don't really feel like touching this area because it's been safe for 50 years. Now, the engineering group, they're going to say, oh, nope, you got to upgrade. You got to put explosion panels in. You need to do venting. That's code. Well, maybe. Go check with your local fire marshal. Check with the EPA. If they believe that in the judgment of the authority having jurisdiction that is reasonably safe and operated, you don't have to upgrade. So these are the things you have to look at when you're upgrading. And every code is this. So that's 61, 69, almost the exact same verbiage. 68, same verbiage. Except for major replacement or renovation. Whose definition of major? Is it a cost? Is it a percentage of your facility? Who defines that major? And then at the 654, same thing, major renovation. and the 652. All of them have the same verbiage in it. So you actually have to go through and decide, when was it written? When was your plant built? What area were you upgrading? Who's going to look at it? Who's going to judge you? Accounting, pretty sure that they don't have the authority. Plant management, they don't have the authority when it comes to the NFPA. Who is it that's going to come down on the facility, on the company? And these are some of the things you got to look at. The engineering, we're going to skip this part. We're going to go right to the meat. And if you ask a vendor, they're going to skip this part. Go right to the meat. When that 652 comes in, those bin bins, boy, you got to have those. So the government regulations, like the lady mentioned in the presentation, 1/8 of dust. This is taken out of the 652's preliminary report. But you see, 1/8 worth of dust is a Class 2 Div 2. You go greater than that, then your explosion hazard. Greater than that, you've got the Class 2 Div 1. And this is exactly what OSHA's coming through the power industry. And if you can write your name in the dust, it's a fine. So they've had to figure out how to reduce this for their Powder River Basin coal. If you got a paperclip thickness, well, they're putting washdowns in everywhere. Washdowns everywhere. Just wash it down, pump it back, settling ponds. You guys can't afford to do that. You wash it down, and there goes your commodity. There goes you can't dry it out and resend it back up versus pumping through. So these are why we're doing some of these government regulations. They're looking out for life safety of the people. So then you ask, what are some of the new technologies? We've been hearing all these new things. It's all about the same. Collection. There's compact and cerebral cartridge types. That's the new buzz. Hey, slap those things on everywhere. That'll solve it. The filter medium that you're using. Well, everyone's trying different coatings. Everyone's trying something different. A HEPA filter, a bag with different type of a weave on it. There is the reevaluate existing systems for better use. Okay, is that really a new technology or just a new way of thinking things? And we'll get to more of that later. Containment. Let's control the dust versus letting it just make the decision where to go. We try to seal things up so much that we pressurize stuff. So we need to stop thinking about the stop, drop, and roll. Stop thinking about how much steel does it cost to go 5 feet to 10 feet. Because we're getting it through the hole faster, but what else are we doing? And in doing that, we're going to talk about discrete element modeling. And that's part of the new technology. Again, it's not really new. It's a technology that may not have been used as much here in the grain industry. We're seeing it a lot in coal mines, iron ore mines, taconite mines, not just for dust, but for wear. But what I like is the holistic approach. You go to a bankruptcy attorney and ask him, do I need to file bankruptcy? He's going to say yes. You go to a realtor and say, do I need to sell my house at a high price? They're going to say yes. So it depends on who you go and ask. You're going to get different answers. So when we're asking about the holistic approach, you got to look at, what are some of these areas we're looking at? What is the holistic? So speaking of the cartridge types of dust collection, they're great because they're single source, all in one, packaged right there. You pick up, you drop off, all right there. There's no extra running. There's usually no supports. It's localized, so I'm going to run power to it. Those are good benefits. They're self-sufficient. They don't rely on another airlock. They don't rely on another blower. They're all packaged right there. No additional duct runs, pneumatic conveying, ease of maintenance. Usually, like we saw in the video yesterday, a little platform, get up, pop that cartridge out, put it back in once it gets up in there. So they're pretty easy. You don't have to go inside a big, lockout, tag-out containment. Makes ease of maintenance, operations. But they're not necessarily the end-all, be-all of the solutions. So slapping one on a boot of a bucket elevator may not be the best spot to put it. On an end of a conveyor, maybe. Depends on what we're doing. So these are some of the things you can put one of these on, pull off some of your dust collection for your main dust collector, and reroute that somewhere else if it seems applicable, if we can reduce the dust to begin with. So discrete element modeling. Some of you guys may ask for a show of hands. Have any of you guys used this, seen it? Got a couple guys? Okay. So basically what discrete element modeling is taking a computer-based program to take the path of the material and project it. And then you get to control the shape of it. where it goes, what it does. You can see these cool little videos. All the salesmen love this thing because it looks great. Really, it does look great on the computer. Allows you to see the effects of a transfer before you build it. You can see where you're going to have wear spots. You're going to see where you're going to have areas wearing out. And of course, half of you guys can say, yeah, I saw that. I knew that was going to happen. You know, and that's part of it is taking this with the field experience that you guys have seen and had and say, yes, that's going to happen. And putting these little balls in motion, because like what we've got down here, this trajectory, we plot this out all the time. And we put these cool little hoods on there. And what you don't see is where these grains and the spread on them wear out. This little program helps you see it. It puts its finite element analysis into the system. So besides what we've always done all, since hand drawings, showing this little cool little trajectory, it goes a little step further. So it highlights the wear points, potential pluggage. You'll actually see, well, not in these videos, but you can make it plug. You can say, if I've got a high cohesion, I'm running something with high moisture content. In these models, you can change the moisture content, and it'll help pull it together. So you can see if it's going to plug and what's going to happen. And we get shape the chute to minimize impacts, turbulence in the grain systems. Dust is generated when it impacts, when it moves. Like they said yesterday, the grain elevators are now in the production of dust. Well, maybe the dust is inside the grain, and every time you disturb that stream, out comes the dust. Every time that hits a wall, hits a spout, free falls through a chute, it helps generate the dust. So once we shape the chute for better flow, allows for less induced air, because the dust is in the air. That's the only way the dust comes out, is when it's in air. If it's in a vacuum, we wouldn't have to worry about it. It would stay all together. You can do the lining impact with the product degradation. So some of you guys, when we're going through for screening and sampling, we want to keep it so we have low breakage, low fraction. Allowing this stuff to slide through with less stop, drop, and roll, better your product is, the better quality you've got. And using gravity to its advantage. I mean, it's here, might as well use it. It's free, might as well use it. So you ask, what does one look like? And this is what we call the silly slide. This is a facility coming up. It's reclaiming coal, but it comes up, and this, if you can't see that well, it snakes down, projects over here, snakes around here, snakes down through here, and comes down, lands on this conveyor down below. So everyone swore this would plug. It's going to slide. It's a silly slide. It's a corkscrew. Well, it hasn't plugged yet. But this is the model they first got. And this is what we generally would have whenever we run one of these. This is the way they originally engineered. A lot of you guys have spouts. Looks a lot like your spouts coming through here. See if it's, there we go. So the engineers put in these cool little balls. This is running, I think it's 1,400 tons a minute, 600 feet per minute, 1,200 tons a minute, 600 feet per minute. These are 4-inch lumps. And we're coming down here, I don't know if you guys can see these numbers here, but 2,500 to 2,700 feet per minute. When you see that blue, it's aerating out. We're running around 2,500 feet per minute free fall. The stuff's screaming. And if this had dust in it, it would just be everywhere. That thing would be so dusty, filling up, plugging the arteries. So the point is, how do we get this slowing down? As we know, we don't want grain to flow past 1,750. So if we're going 2,700 feet per minute, we have breakage, we have dust, we have wear, we have impact. We're creating dust. We don't want to create the dust. So you can see here, we run this. You guys know that you'll be putting wear plates in the back of this place here trying to stop this. Every spot you have a wear, you have a dust generation point. So if we stop the wear, we can stop the dust. We don't have to collect as much. If we have to collect as much, we can reroute some of the existing dust collection to points that need it, that have to have it. So each transfer, maybe we need to relook at these things. When we come down and load the belt, this induced air is sucking down through here, and it's got to go somewhere. That induced air comes out of here. As you guys know, when you fire it up, out those skirt boards, plume of dust. And as it's coming through, that induced air that we're sucking down through here is coming out. You've got to do something with that induced air. You've got to suck it up. You've got to slow it down. But in that induced air is dust. So this is the model after we created it. Now if you watch, this is actually, we try to make it somewhat real. You'll see some spillage. But we're only running 1,700 feet per minute. Exact same height, exact same tonnage, just different shape chute. 1,000 feet per minute less by changing the shape of the chute. And again, they're like, it's going to plug. 1,700 feet per minute, it's flying along. It's cruising. It doesn't have time to slow down and plug. You can see spots where you may have some wear points. You see your transfers. The spot we had the impact before, it's not as high. We're still going to have some, but it's now at a vertical spot. We're catching it, and it's in a sliding motion. We're controlling that. We could even change this spot down here so we make it so it lands on the dot at 800 feet per minute. And you don't have the turbulence, the roll that you always see on these conveyors. We have the aspiration at the head and the tail before and after the loader. Because we're creating so much dust, we've got to suck it off the back end, and we have to suck it off the front. Well, you make this so it goes down and slides on there, take that dust collection there and move it somewhere else. So that's what do these things really look like. Here's the manufacturing of them. Usually you got an adjustable hood so you can catch that trajectory, because no matter what, as you guys know, no matter what you engineer, doesn't always fit in the field. Got to have some adjustment. It looks great on paper, but you have to build these to have some adjustment. The modeling is only so good as what the person put in. And I highly suggest that you get somebody in the field to go over this. The guy running the computer may run the computer great software guy, but he needs your help to know what this material is really going to do. You guys have years of experience knowing how it's going to impact, how it's going to wear, how it's going to slide. The model can only do so much. So we've got some nice cool hoods that pop off. You've got some transfer chutes coming down to maybe a spout, to a truck loading spout, or a barge loading spout, or a ship loading spout. But you got to have some adjustment in there. By doing this, we can help reduce air, aids dust. So every time we come through there, we're dragging along the dust. You guys know it, you see it, that's why we put the little rubber curtains around the top and bottom. If we can stop that, this is what's happening. You bring the dragging air through here, it displaces the air in the chute. When it's empty, it's quote empty, but it's full of air. When you put material in it, just like your bucket elevator cups, those cups are coming up empty. You put grain dust in those cups, air's got to come out. Air coming out, dust comes out. Same thing with the belt conveyor. When we come out, we're inducing this air. We're creating this turbulence. So how can we stop dragging all this air with us, letting it separate out? So if we control the open air of the chute, it limits the air intake that generates the dust. It keeps the material from spreading out and releasing the dust. Helps keeps it in. Smaller can be a lot better. For a while, everyone's making the chutes bigger because they kept plugging. Well, did they keep plugging because they were too small? Or they keep plugging because we kept getting dust buildup and dust buildup and dust buildup because we had to reaccelerate the velocity, and it started from 0 and went back to 1,700. So smaller, we have found, has been better when designed properly. Designed not properly, smaller's not better. Controlling the shape of the chute. A great pitch and catch allows for the moment to continue, the momentum to continue. I mean, when you're coming through and you come through a curve, you can keep that angular velocity coming down. You keep this going on. The proper shape allows scouring. And on this next slide here, I'm going to ask if anyone knows what this is and why it's important. Does anyone know what this is? Pardon? Which plow? John Deere plow. That's right. And why was this so important? Why was this particular John Deere model so great? Exactly. It's because he shaped this and it scoured it to shed the dirt. Prior to this, people would have to stop by and clean this thing off. Well, I can put an angle in the ground and create a little V and move dirt, but the correct shape of this plow has made it so you can move through faster. So why does this plow stay clean going through the dirt and the other ones didn't? It has to do with the shape of the plow, shape of the sweep. So a lot of this is forgotten in some technologies. Wait a minute, snow plows do it, plows in dirt, and I think putting your plow down in the dirt is a lot more harder than material going through a chute transfer. But yeah, John Deere's first plow, because he made it shaped correctly to scour off the dirt. So when do we evaluate these needs? When do we evaluate the new methods? Housekeeping issue arises, you're spending more money on maintenance, cleanup, you're getting too much dust return, upgrading your equipment. Hey, capital improvement. They come along and say, hey, we're going to upgrade the bucket elevator or the belts. We've got open belts, and we want enclosed belts now. Well, now's the time to look at this as well, because when you do that, you have to do your transfers. You just don't cut it off with your old belt and put in the new and closed belt and keep that same transfer. The belt conveyor can do the capacity, only what gets in and what gets out. If it can't get in, it can't handle it. If it can't get out, it can't handle it. So we want to increase capacity. Farmers are shipping more. They're bringing in more. Trucks are lining up. So more also means more dust. You want to increase your capacity, help minimize the dust. And of course, an accident. We really hope that's the last reason why we're upgrading is an accident. We want to do it for the right reason, not wait for the last reason. So when we're looking at where, I'm a huge believer in stopping the dust, the transfer points. At every point, whether it's truck, train, vessel, you got a pit, conveyor to conveyor, via chutes or spouts, conveyor to elevator, chutes and spouts, loading spouts. Most of you guys probably know this. Some of the engineers probably don't, I've learned. If you look at your belts coming down from the receiving, and it's a long belt, it's traveling along, and it's going, and it's coming out of the band, it's all mixed up in there, it's really great. But all that dust settles to the bottom of the belt. So when that stuff shoots off that trajectory, boy, in these cool little programs, you'll see all those little pellets, and they go around, they look like they're going great. But that bottom layer is full of dust. And that transfer, it gets filled with all that dust. So here's a typical old style. A lot of people still have these. You suck off the head. And you suck off over here. And they don't show the one back here, but they have one here because you create so much turbulence. And everyone still believes that we got to suck off the head of the conveyor. But if my material stream is coming through here, and I got the big stuff on top, and all the dust on bottom, how am I sucking that dust through that stream? So why am I sucking this dust off the top here when I'm trying to suck and come around here? Oh, that's right, because I've impacted, I stopped the momentum, I've blown it up, I've made air go everywhere, now I've made dust go everywhere, so yeah, now I have to suck it off the head. Well, if we stop that stop, drop, and roll, and keep the dust where it needs to be, I can move this dust collection from here down to here, or somewhere else. This is more along the chute, so that we see here, we don't have too many rock boxes in the grain industry. But you've got this turbines. When you look in your head chute, you see this boiling, I like to call the boiling up here. Well, that boiling is creating your dust. The boiling is inducing the air. So this doesn't show, but there should be a dust collection here, and here our dust is coming down, and this dust isn't hitting the belt speed at 800 feet per minute, so it's going to turbulence, and so I got to put dust collection back here, and now I got to put one up here, and I just keep treating the symptoms. Let's try treating the problem. So when you run these things, you can also look at the loading of, this particular model is a loading of the spout, and they're comparing a straight back hood versus a curved back hood. So even just changing the hood design, and not necessarily the long silly slide, making it curved and fancy and sexy, but it's still nice to have that, just changing the shape of the hood. This is easier to manufacture. Yes, it is. This, over a long period of time, will be easier to maintain. You have a huge impact here. You can see our high wear spots. While we have the wear spots here, the red shows where we're having turbulence. We're impacted here. You see the stub material stop. When it's red, it's stopped. When it's yellow, it's slowing down. We've stopped here, and we are impacting the end of this spot. Here, we're catching it, and we're making it slide down. This facility is running 4,200 tons an hour of coal through a 36-inch diameter spout. Now, most rules of thumb say we can do 75, 77 bushels per square inch. If you're flying out everywhere, yeah, you need to have that kind of space to suck it down so it doesn't plug. But if you keep it consolidated, skiving the walls like the plow, keeping it focused in, it's just all you do is turn that material stream, your cross-sectional area of your belt. It's almost like you're taking it off the belt and straight down. We're not stop, dropping, and rolling again. So when we look at this stuff, not only does it show us what we can wear, we can plug, you can simulate where we have issues. And this is it running, showing the cool little ball bouncing. Like I said, this a lot of people like the little cool videos of this. But again, this needs coupled with experience. This is only a computer program. So what you see here, if we're coming off, it's shooting down. You'll have a little bit of dust here, but the more we can keep this and capture it right off the head before we stop, drop, and roll, gravity's already there, so let's keep that momentum going. Let's start using gravity, because we already know that in the first 10 feet, we're going to reaccelerate over 900 feet per minute. So in this example here, by the time I hit the bottom, we're already at 1750. We're at terminal velocity for grain. And you're in a spout, load spout, barge spout. You can't really slow it down that much. But you can stop the degradation and the dust generation at least in that first 10 feet. So at least help yourselves with wear and get through this first part. Plus, you get a smaller spout. Smaller spout, less weight, less wear, less cost. Go to the spout manufacturer and ask him what he wants. He's going to give you bigger. Bigger's better in his mind. And sometimes it is. Depends on what you're doing. But if we can make it and turn it, then let's make it smaller. So that's why I look at the holistic approach. We've got upgrades. When you do it, you can go back to hooking up your old dust collection. You can say, how do I stop generating that dust so I don't have to collect it? And then if I don't have to or where I have to, what is the best one? Is it an insertable? Can I take my big beast and say, you know what? We've chopped this thing all over the place. I'm going to actually cut this back to what it was originally designed for. So determine what must be done versus what's suggested. What really has to be done. So do I have to put in new insertables? Do I have to put in a new dust collector? Do I have to put in a new conveyor? Some people say, well, I need a $100,000 dust collection system. Maybe. Or maybe if we control that dust and we put it down slide, you don't have to have a whole new dust collection. You can settle it out, making distilling chambers coming down, knocking it out through the dust curtains. Knock the dust out of the induced air. Determine what agency is going to have the jurisdiction. So do I have to upgrade to explosion panels? Do I have to upgrade to dust collection? Why am I doing this? And where are we going to get, possibly fined? We don't want to get fined, but where we have evaluate the existing collection for inefficiencies. Maybe you load your screening and your dust load at the same time. But sometimes some facilities have changed operations since that original design, and they no longer go through screening or go through bulk weighing when they're doing the truck loadout. And so now I can say, wait a minute, I can put a baffle in here and take that dust collection over here and put a negative pressure on my truck loadout. Drop some curtains down around it, and I'm carrying a negative pressure so that I don't get the dust outside of my truck loadout area. So I'm not, I'm being a good neighbor. So maybe I can still use my existing facility versus put in new dust collection. Operations may have changed. Check with the operators. They know what the system is. A lot of times when us engineers, we look at the drawings, we're like, oh yeah, this makes sense. Or I don't understand why they did that. Check with operations. They can tell you why it's like this or why it's been changed. High-speed transfers have dust collection at the top and bottom. If we collect and move this like we've shown, now I can use this dust collection somewhere else. Maybe I can use it on my truck loadout. Material containment, why reload if you can keep it already loaded? Enclosed belt conveyors keeps everything in there and keeps the dust and reloads it back up. Going through a transfer, when you start wearing a hole in your chute, why not keep it in the chute versus have to have maintenance where you clean up? Your cost of cleanup, your cost of maintenance, as you guys know, goes up every time you have a spillage. Slows you down. So let's keep it on the belt. All right. So we've got to evaluate the existing dust systems. So we eliminate the reduce of what causes the dust, reduce the requirements for collecting the dust, local containment. Using this approach can have the amount of dust collection design methods versus the rules of thumb. Rules of thumbs are great, but we have computers. So let's try evaluating this more. Evaluating existing collections for extra capacity, like I explained, the dust loadout, the truck loadout, where can we change these? And evaluate the existing collections for extra capacity. There's several different ways that can be done, but only with your guys' help. Don't always let the engineers decide what's the best. Help them decide what the best is. A team approach. So we got to think on the edge of the box, not outside the box. If we stay inside the box, we may get something like this, like a Model T Ford. That's the best car ever built, in Henry Ford's opinion. Why upgrade? If you think way outside the box, you're going to be a flying saucer. And if you think you're a wacko, somebody just screwed down what Model is. But if you think right on the right edge, you could be a Nissan GT-R, a V6 that can outperform an Audi V10. So that's why you need to take a holistic approach.
Do we have any questions for Andrew?
On the NFPA 61, and actually with all those rules down there, the second line in that, which was 1.4.2, it says the authority that has jurisdiction, if it feels there's an unacceptable risk, enforcement.
Correct.
Okay, who defines unacceptable risk?
That person.
That's the problem.
Exactly, and that's why it's always good to be, nice with them, because they can also go the other direction where it says at the bottom, if they feel safe enough, you don't have to comply. And that's where it gets down to, it's almost an individual's opinion. Absolutely right.
Any other questions? You want to step up to the mic? It's probably not on.
But step into it anyway.
I'll just talk loud. Does the spout have to be a certain length for it to be more effective?
Yes and no. There has to be enough distance to get your trajectory to turn. Drag conveyors is probably not an application in the speed. When you get more than, anything usually over 3 feet, then you can do almost a continuous hood and spoon. The longer you go, the more important this is. So on your spouts, on your coming down off of a bucket elevator, maybe to a turn head, or that's you going out to a truck or rail load out, those are some critical areas where you can help slow it down. Inside the building, you can help it by just putting in a curve and catching it, and then spooning it. I mean, we've done it as close as 5 feet on a pitch and catch. So it can't be slammed up against each other, and the more you rotate, if you're going 90 degrees, they make these cool swoop ones, and you put it all into one. So while you're not directly on top, there is a height limit just to be able to get the material to turn and the radiuses.
Has it ever been used in barge loadout?
Yes, well, in grain,
Yeah.
no. The one you just saw on there was a coal loadout, yes.
And it reduces the amount of dust, because, EPA, if EPA hasn't visited you on this, they're headed your way.
Yes, they are.
Because they're looking at the amount of dust that's coming out of the barge, and so.
Yeah. This, what it helps, it helps reduce the initial dust that's coming out. As, on a barge, the operator is probably the key guy in adjusting that dust, staying right there off of that level, that height amount. But the more you can keep that down and focused, the smaller spout you can get, the less you spread out when you hit the bottom, so less dust you generate. So that's where it does help it, but it can't, once you enter the spout, on a telescoping spout, on a fixed spout, it can really help reduce that amount by the amount of reduced air that you have in there.
Okay.
Anyone else? Okay, well, let's give Andrew a round of applause.